We now take a look at a couple of companion problems at the end of Chapter 5. The first one is actually a conceptual problem. We're given a circular plate with a weight. It's supported by a chord DE and a thrust bearing at B. We'll take a look at the figure below in just a minute. We're told the shaft on which the bearing is mounted is fixed and frictionless. We first want to draw the free body diagram for the plate, labeling all forces and moments, including all the reaction components. And then before we actually get into the details of solving, we want to rate the solution strategies, and there's 5 listed below, in terms of the ease of obtaining the magnitude of the tension DE in the cable. We're told to rate the best choice as number 1, second best as 2, and so on, and if a solution strategy does not work, then label it with a 0. For reference later, I'll number these as 1 through 5. The second part of the problem, which is 5.1.11, is to then actually employ that best solution strategy to solve for the tension TDE. Take a few minutes now to try this problem yourself and resume playing when you're ready to see a solution. I'm going to represent the reaction components directly on this figure. We'll begin with the free body diagram. We've got a cable that's pulling from D to E. So I'll represent that force component here, and that's going to be vector TDE equals magnitude TDE that we're trying to find on a unit vector from D to E. We're also going to have a total of 5 reaction components at B. This is a standard bearing. It's got a thrust component, so there will be a component of force parallel to the bearing's axis. And because the bearing gives us the ability to rotate about the shaft AC, it will make the most sense to represent reaction components parallel and perpendicular to that shaft. Now the shaft AC lies in the YZ plane, and actually we can see from the geometry something about that orientation. So we can see that we've got a rise of 10 over a run of 22. Basically we've got 2 increments of 5 and 12. So this is going to form a 5, 12, 13 triangle in the YZ plane. That's going to be useful for us shortly. And now in terms of the reaction components, I'm going to give the thrust bearing a label B parallel. One of the force components normal to this shaft will be along the x direction since AC lies in the YZ plane. So I'm going to represent that as BX. And then the other normal component will be perpendicular both to B parallel and to BX. It will be in the YZ plane, but it will have a slope that is the negative reciprocal of that 5, 12, 13 triangle we just sketched. I'm going to label that as B perp. So let's just make a note that for the force components that I've labeled there at B, we've got BX obviously is in the I direction, B parallel is aligned with U parallel, which is going to be minus 12/13 in J and plus 5/13 in K. And then B perp is going to be aligned with U perp, which again is going to have the negative reciprocal of that slope, and that would make it 5/13 J. Okay, now we're also going to have moment reactions. This is not a self-aligning bearing, and so we'll have an MX, and we'll have an M perp. So we've got these 5 reaction components at B. So let's note first that we've got 6 unknowns. We have TDE, and we have the 5 reaction components at the bearing. And that suggests, with a number of unknown reaction components of 6 and a number of equilibrium equations of 6, that suggests that we have a statically determinate system. So in all of these proposed approaches, if they're legitimate approaches, we should be able to solve for the unknown reaction components, and we probably have full fixity. So now let's consider each of these proposed approaches one at a time. The first one, we have sum of the forces equals 0, and sum of the moments about B equals 0. This will work, but the question is, what's the degree of complexity of the system of equations that we'll have? When we take moments about B, none of the force components, Bx, B parallel, or B perp, will appear in our moment equation, but the moment reactions Mx and M perp will appear in addition to the tension at dE. So what that tells us is that this is complicated by the fact that sum of the moments about B equals 0 produces three equations in the three unknowns Mx, M perp, and TdE. So that's not a bad choice, but if possible, we'd like to find something simpler. The second proposed approach asks about writing the cross product RBF cross the weight plus RBD cross the tension equals 0, and then to solve for TdE. If we think about sum of the moments about B equals 0, what would that look like if we wrote that out? That would be RBF cross the weight plus RBD cross the tension in dE. And then we have the moment reactions we have to add. So we have to add plus Mx and I and plus M perp along U perp is equal to 0. So here the proposed approach represents an incomplete moment equation about B and is incorrect. So this won't work, and when we get back to rating this, we'll give it a 0. The third approach suggests sum of the forces equals 0 and sum of the moments about the origin equals 0. Now again, we can choose to take moments about any place we like, and certainly this approach will work. The question is, how complicated is it? So this will work, but it involves even more unknowns, even more coupling than in the first case. In particular, sum of the moments about O equals 0 will involve all 6 unknowns. So while this is possible, it's a really inefficient way of solving the problem and one we should probably avoid. The fourth proposed solution involves taking the dot product with a couple of cross product terms, and this actually will work for reasons that will be apparent if we go back to our moment equation about B. So now I want to consider the following equation. I want to take sum of the moments about B equals 0, and I want to dot that into U parallel, which is the same as dotting it into RAC in the proposed solution. We previously wrote out the sum of the moments about B equals 0, and I'll reproduce that here. So now if we take this whole equation and we dot it into U parallel, what happens? Well, given the coordinate system that I have defined at B, I dot U parallel is equal to U perp dot U parallel, which is equal to 0. So now the fact that I have these two moment reactions in our moment equation doesn't really matter, because they'll go away when I take the dot product between this unit vector and the whole equation. And what I will then be left with is what's essentially proposed in the problem statement. I'll have RBF cross the weight plus RBD cross TdE. I'm going to dot that into U parallel, and that will give me one scalar equation in the tension that I'm seeking. So this is the best or most efficient approach of any proposed, as it will turn out, to solve for the tension in DE, because when I'm done, I'm going to have one equation and one unknown. Finally, in the last approach, we have sum of the forces in F equals 0 and sum of the moments about D equals 0. Again, this will work, but this is only slightly better than case 3. Why is that? Well, if I take moments about D, the tension in DE won't contribute anything. Will involve 5 instead of the full 6 unknowns. The one unknown that isn't involved is the tension in DE that I'm actually seeking. But once I get that, I can use the results to get the tension in DE from the force equations. So I don't know if this is really better or worse than case 3. The moment equation has one less unknown, but after we solve for those unknowns, then we have to go back to the force equation to solve for TDE. So if I go back to my original statement and we rate these, first we'll give 2 a 0 because that won't work. That represented an incomplete moment equation. 4 represents the best. It will work and involves a single scalar equation and one unknown. And now instead of ranking the remaining 3 as 2, 3, and 4, I'm going to put larger spaces between these to reflect the additional calculational difficulty that would be involved with pursuing any of these options. So I'm going to give 1 a 3. It's going to involve 3 unknowns when I write my moment equation. It's certainly doable. It's not a bad choice, but it's just not the best choice. And then I can't decide whether 3 or 5 is worse. We can, again, take moments about any place that we like, but these are really inefficient places to do so. It's going to give us systems of equations that are really complicated. So I think I'm going to give both of those a 10, just to indicate that it's kind of a tie. They're both substantially more complicated than 1, which is itself more complicated than 4. So that would be my choice. Okay, so now that we've decided on our solution strategy, I'm going to go back to my free body diagram, and I have added a couple of different points. I've added B, which is in the YZ plane and has coordinates 0, 12 inches in J, and 5 inches in K, and point E, which is at 0, 0, 21 inches. We now want to construct the appropriate relative position vectors and take this dot product and solve for the tension in DE. So let's just make a note. I could write RBF as RF minus RB, and that would be 5I plus J inches. And I could write RBD as RD minus RB, and that's 9I plus 6J minus 2K inches. We're also going to need RDE in order to define a unit vector that goes from D to E, and RDE is RE minus RD, and that's minus 9I minus 18J plus 18K inches. And this relative position vector has a common 9 between those 3 components. A vector 1, 2, 2 has magnitude 3, and it will turn out the unit vector that goes with this is minus 1/3 I minus 2/3 J plus 2/3 K. So on that basis now we'll start carrying out the details. We have RBF across the weight, which is 5I plus J inches crossed into minus 200 pounds in K, and I cross K turns out to be minus J, so we end up with our first term is 1000J, and then J cross K is equal to I, and we end up with minus 200 I inch-pounds. For RBD cross TDE, that's a little more involved, so I'll use the matrix approach. And I will pull the magnitude TDE out in front down here and use the unit vector inside. RBD is 9, 6, and minus 2 inches. And the components of TDE are minus 1/3, minus 2/3, and plus 2/3. And when we put all this together, we get, in the I direction, we get a 12/3 minus 4/3. We get an 8/3 I in the first component. We get a minus J, that's 18 minus 2, or minus 16/3 J. And in the K direction, we get a minus 18 plus 6, which is a minus 12/3, or minus 4K. All of this times TDE inch-pounds. So now the RBF cross the weight dotted into U parallel will be minus 200I plus 1000J dotted into minus 12/13 J plus 5/13 K. And the only thing that survives from that dot product are the J terms. That ends up being minus 12,000 over 13. And for the RBD cross TDE dotted into U parallel, we have the 8/3 I minus 16/3 J minus 4K TDE dotted into the same unit vector. The I component contributes nothing. We get a 16/3 times 12/13, and that ends up giving us a 4 here, which ends up giving us 64 over 13. And in the K components, we've got a minus 20 over 13 times TDE. So when we put these things together, the sum of those two components is equal to 0, and that means that this has to equal 12,000 over 13. And that gives us a tension, TDE, of 12,000 over 44 pounds, and that number turns out to be 272.7 pounds. In summary, a lot of these three-dimensional problems, even for a single rigid body, are quite complicated because we have 6 scalar component equations. If it's statically determinate, we're going to have 6 unknowns. It really is useful to consider, before we start doing anything, different options for how we solve problems so we can get to our solutions in the most efficient manner possible.